Okay, so we're going to continue on here, chapter 4. So the other day I did post a recorded lecture, the first little part of chapter 4. So we're going to pick up after that. Again, make sure, hopefully you watched it. If not, make sure you do. I think it's only like 36 minutes or something like that. So in this chapter, we're going to talk about atoms, obviously. And in that first part of the lecture, we talked about sort of the important experiments that led to our understanding of sort of the modern atom. And again, just to review some of those things out of that video, really all of it started with kind of early on Dalton's atomic theory, where he really laid out sort of the idea of what atoms are, how they sort of behave, and how they interact. And as we talked about there, not all parts of Dalton's atomic theory are still correct. There's certain things we'll talk about in this chapter that sort of disprove parts of it. For example, the idea that all elements have atoms that are identical to each other. And again, the existence of isotopes, which are the same element, that have different masses, basically kind of disprove that point of it. Some of the major sort of understanding of the atom, which obviously contains protons, which are positive, electrons, which are negative, and neutrons, which have no charge. Early on, the cathode ray tube was used by Thomson and others to really explore the electron and some aspects of the electron. Sort of Thomson's experiments with the CRT tube and the oil drop experiment, which was done by Milligan. Basically, these two sort of experiments together gave us the sort of charge, the mass of an electron, and also the charge of an electron. And really from that, we're able to determine the mass of an electron. And it was found to be something like 0.09 times 10 to the minus 28 grams, which is a fairly small number. These sort of early experiments and the idea that they had at the time that the atom was basically neutral, and the idea that electrons obviously are negative, that there had to be some type of positive component there in the atom, basically to balance out the negative charge. And an early model of the atom was the plum pudding model that was set forth by Thomson. And in the plum pudding model, basically the atom is a sphere of positive charge, and we have electrons that are basically embedded inside. And it was thought that most of the mass of the atom was made up of those electrons. And this was sort of the accepted model of the atom until really the next kind of big experiment that came about that we talked about, which was Rutherford's gold foil experiment. And that was done by Rutherford. And Rutherford shot these alpha particles, which are positively charged radioactive particles, at pieces of gold foil and other metals. And based on the idea of these heavy moving and fast moving positively charged alpha particles, they expected kind of when they went through the atom to basically sort of be deflected. Again, the idea is, as we also talked about in that sort of lecture, positive and negative things are attracted to each other, but things that have the same charge are repelled by one another. So things that are positive and positive do not want to be near each other, and things that are negative and negative do not want to be near each other. So they anticipated that when they did shoot these alpha particles at the atom, that most of them would go through. There would be some deflection as it went through because it's positive on positive, but it is moving really relatively quickly. What they actually saw was kind of surprising to them. They saw that really most of them kind of shot through with no problem. But they did notice that every so often there would be some alpha particles that would be scattered at these really sort of large angles. And what that really told them was, in order for it to kind of make these heavy moving and fast moving alpha particles really scatter at those large angles, it had to hit something that was really, really positive. So they really had to abandon the early model of the atom here and sort of come up with sort of a revised model of it. And basically what they said was most of the atom was empty space. And that basically accounted for why a lot of those alpha particles sailed through with no problem. They just went straight through because frankly, they didn't hit anything. They didn't come across anything. They kind of went through empty space. They also felt that it did have a dense positive core, which is the nucleus. And that accounted for why these alpha particles were able to be really scattered at these really large angles. They had to hit something that was very, very positively charged in order to scatter it at those really large angles. They also said that most of the mass of the atom was actually the nucleus. As later sort of experiments discovered, both the proton and the neutron were about 1,800 or so times heavier than any electron that's flying around. So both protons and neutrons are much, much heavier than an electron. With, as we saw in that lecture, the neutron like barely edges out the proton as being the heaviest. So it's really the neutron that is the heaviest. The proton is the next heaviest. And then the lightest of all of them in terms of mass is the electron. So this is important because of the location of where we have our particles. We have our protons and we have our neutrons that are in the nucleus of an atom. And out in that empty space, really flying around in a random pattern. And as we'll talk about in a later chapter, electrons really don't move in nice circular patterns or anything like that. Their motion is really sort of random about the nucleus. But there is some attractive force between them, as the nucleus is really positively charged, electrons are negatively charged. So there's definitely some attraction that keeps the electrons from just kind of flying off, but they really don't move in these pretty circles. So this idea that the nucleus was most of the mass of the atom does make sense based on the idea that protons and neutrons, which are found in the nucleus, again, much, much heavier than any electron that's flying around. Any questions on any of that stuff there? So here's sort of a model of the atom. Atoms, although they're really small, the nucleus is even smaller, but does contain most of the mass of it. This is what's sometimes referred to as an electron density diagram. Kind of the darker areas is a higher probability of finding electrons. The lighter is a little bit less of a probability. So we have our protons and our neutrons in our nucleus. We have our electrons really flying around sort of the space here. And again, there is definitely some attractive force between the electrons and the nucleus, but they don't travel in pretty circles. And again, here, as I talked about 1,800 or so times heavier are protons and our neutrons, with our neutrons obviously being the heaviest. Electrons -1 charge, +1 charge for our protons, and then once again our neutrons, which was discovered in 1930s, have no charge. Any questions on the atom there? Now, most of the chemistry, as we've talked about perhaps before, does come from electrons. Pretty much all chemical reactions, really the only thing that happens is we pretty much break bonds and make bonds, as we talked about. And that really just involves electrons. So in a normal chemical reaction, it's just all about the electrons making and breaking bonds. They're involved in the recombination of new things in a chemical reaction. Really, in normal reactions, chemical reactions found in the nucleus really aren't involved. So no protons or neutrons are involved, just electrons. In nuclear reactions, you do get protons and neutrons sort of involved, but not in normal chemical reactions. Some other aspects of atoms that we want to talk about, we have atomic number, mass number, and isotopes. So let's talk a little bit about each of these and what they are. We're going to start with the atomic number. The atomic number is sometimes abbreviated with a Z. The definition of the atomic number is the number of protons that there are in an atom. Now, if we have something that is neutral or a neutral atom, obviously, since there's only 3 particles that make up an atom, protons, electrons, and neutrons have no charge, and protons are positively charged. So in order for something to be neutral, you would need the same number of electrons. So if you have a neutral atom and you know the atomic number, or you know the number of protons, which is basically the same thing, you will also know the number of electrons. It should be the exact same number. So all the positives and negatives cancel each other out. It is important, though, that if you are asked a question of what is the definition of the atomic number, the definition of the atomic number is just the protons. So that is the actual definition of atomic number, just the number of protons there are. But again, in a neutral atom situation, it will let you know how many electrons that you have. We can find the atomic number right there on our good friend, the periodic table. And we look on the periodic table, like, for example, lithium, and we look at the number above. That is the atomic number. So lithium would have 3 protons. And if it is a neutral lithium, it should also have 3 electrons. So 3 positive guys, 3 negative guys equals 0, gives it no charge overall. If you look at the periodic table and all the numbers that go there, there's actually one up here as well. So if you look at the numbers there on top of the symbols, you will see that none of them repeat. Numbers repeat, and that's really an important thing. It is the number of protons, which is the atomic number, that determines what element you're dealing with. So again, if you know the protons, which is the atomic number, you will know exactly what element you're dealing with. You could just go to the periodic table and find that number. So if we had something like 12 as the atomic number, so if we had an atomic number of 12, we could go to the periodic table and we could find magnesium as number 12, and that would be obviously the element we're talking about. And if it was a neutral magnesium atom, it would have 12 electrons and 12 protons to balance it out. Just like we see there on the bottom, number 7 is nitrogen. So 7 for nitrogen means it would have 7 protons, and if it is neutral, it would also have 7 electrons in that case. You will never ever have a carbon atom that has, 8 protons. Will never be carbon, because carbon has 6 is the atomic number. 8 would be, if you went to the periodic table, oxygen. So again, if you change the number of protons or something like that, you do change the element that you're dealing with. And every element has its own number of protons and an atomic number. Any questions on that there? Another important number is the mass number. And the mass number is the number of protons and neutrons there are in an atom. And that's really important when we deal with the mass number and the atomic number together. Because if we take the mass number, which is our number of protons plus the number of neutrons, and we take the atomic number that we were just talking about, which is the number of protons, and we subtract them, the number of protons cancel, and you can figure out the number of neutrons. So if you take the mass number minus the atomic number, it will tell you the number of neutrons that there are. Now, every element will pretty much have protons, electrons, and neutrons. The exception is hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron, but everybody else will have protons, electrons, and neutrons, why hydrogen has some unusual properties as well. When you calculate the mass number, the atomic number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. So, for example, when we look at something like on the periodic table, the number underneath this number, is that the mass number? That number is not the mass number. And the way you can remember it is it needs to be a whole number, and that is clearly not a whole number. And if you look at the periodic table, pretty much everybody has a number underneath it. And that number underneath is pretty much a decimal number for everybody that is there. That is actually the atomic mass, which we'll talk about as well in another chapter. And it is not the mass number. What confuses a lot of people is this. The atomic mass and the mass number oftentimes are numbers very close to each other. So sometimes people look at it and go, oh, that's the mass number. So the only number that you can find on the periodic table is really the atomic number. If you need to calculate the mass number or the number of neutrons, the problem should give you enough information to do that. And again, it should be a whole number. So do not use the number on the periodic table on the bottom as the mass number. You find yourself writing it as a decimal and using that number, you probably should cross it out yourself because it will end up with an X. Yeah, so do not use it for the mass number. Any questions on that there? Now, isotopes. Isotopes, as I mentioned a second ago, are really the same element, but they do have different masses. So because they have to be the same element, they all have the same atomic number. They all have the same number of protons, because again, if you change the protons, you change the element. What gives them different masses is they have different numbers of neutrons. So because they have different numbers of neutrons, they will have different masses. So for example, hydrogen has 1 proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. And tritium, which is like the radioactive version of hydrogen, has basically 1 proton and 2 neutrons. A very common way that we write symbols to represent isotopes, including their mass number and atomic number, is we use the symbol, and top left is the mass number, and bottom left there is the atomic number. So that is a very common way that we do it. So for example, if we were going to do it for these 3 guys here, these 3 isotopes, perhaps you didn't know what hydrogen is, but when you see 1 proton, what you need to do is pretty much go to the periodic table, number 1, and you see that the symbol is H. And you also see that the atomic number is 1, which would go on the bottom left. And for our mass number, 1 proton plus no neutrons gives us 1 in terms of the mass number. So that would be the symbol there for the isotope of hydrogen. Now, maybe you come across deuterium and go, I don't know what element that is, but you will know what element it is by looking at the number of protons. And again, you see it is 1. So you just go to the periodic table and find number 1, which again means you would use the same symbol because 1 is hydrogen. In this case, though, we have 1 plus 1 in terms of protons and neutrons, gives us a mass number of 2. And that would be the symbol there for the deuterium isotope. Once again, tritium doesn't sound like hydrogen, but because it does have 1 proton, and you go to the periodic table, find number 1, it also will use the hydrogen symbol. Also will have an atomic number of 1. And in this case here, 1 plus 2 gives us 3 in terms of our mass number. So these would be the way that we could write the symbols, including the mass number and the atomic number for isotopes here. Again, basically, if you subtract the top number from the bottom number, gives you the number of neutrons. So if we take 1 minus 1, 0, 2 minus 1, 1, and 2, I wrote that should be 3. Bad writing there. 3 minus 1 would be 2 in this case, would give us our number of neutrons. Any questions on that there? Now, a common way that isotope symbols are sometimes written, for example, like Fe59, right? So Would this 59 be the atomic number or the mass number? What do you think? It would be the mass number, and we know this because if we went to the periodic table and we looked up iron, which is Fe, we would see that it is number 26, which would be its atomic number. So if we were to write sort of the different formula or way of writing the expression, Fe with 26 on the bottom, 59 would go up on top. And obviously, if we subtracted that, we would end up with 33 neutrons. Yeah, in this particular case. Any questions on that? And that would be 59 minus 26 would get us our 33 neutrons. Question on that. All right, so why don't you try some here? We were looking for how many protons, electrons, and neutrons there are in each of the following. All right, so take a couple of minutes here and see what you come up with for each of these. First off, CO's cobalt. Again, top left here would be our mass number, which is our number of protons and neutrons. Bottom left here would be our atomic number, which is just our number of protons. So in this case, we would know cobalt here should have 27 protons, right? Now, this particular one is neutral, and the reason we do know that it's neutral is, frankly, there is nothing written here, so there is no charge or anything written. So if there was some type of charge, like a +3, -3, whatever it may be, it would definitely be written there. So if you don't see anything, you could assume that it is neutral. So as we talked about, because really the only other thing in the atom that has a charge is our electrons, because it has to equal neutral and be 0, we would have an equal number of electrons, which would give us an overall charge of 0. Yeah. Yeah, we'll actually talk about some in just a second that has charges. Yeah. Other questions? Now, in terms of our neutrons, we will have our mass number, which is 60, minus our atomic number, which is 27. And it would be 33 in that particular case. Any questions on that one there? All right, looking at Cl, which is chlorine. Once again, we do not see anything written there in terms of a charge. Our bottom number, which is our atomic number, is the number of protons. So our number of protons here would be 17. And once again, because it has no charge, it will need an equal number of electrons to basically zero it out. And now for our neutrons, we take our mass number, which is the top number, 37, minus our bottom number, which is 17. And that looks like 20 in terms of our neutrons. Lastly, on this one, we have U, which is uranium. Once again, no charge. So we're going to look at our atomic number that we could get from the periodic table. That tells us that this uranium atom has 92 protons. And the number of electrons in that case would be also 92, which would again zero you out in terms of the charge. And our number of neutrons, 238 minus 92, that's a lot, like a 146er, I think, would be the winner there. Any question on any of those there? All right, let's try a few more here. Let's actually write the symbol. So we want to write the symbol with the mass number and the atomic number associated with them. So for each of these here, and actually we'll change this one since I kind of jumped the gun and did that one. Let's do calcium. And let's say calcium had a mass number of 40. So we'll do that one since we kind of did that one earlier. All right, so for each of these, write the appropriate symbol with the mass number and the atomic number that you got going on. Okay, let's take a look. So once again, we would go to the periodic table to help us out here. And if you did, you would find krypton there as Kr. That would give you your symbol. The other important thing it will give you is the atomic number that we can find. And in this case, it is 36, which should go bottom left. Now that 36 also tells us that is the number of protons. And here they told us that the number of neutrons was 48. So that's going to give us an 84 as our mass number when we add it together. And we should end up with something like this. Any questions on that one there? Same thing here. We go nitrogen, find it on the table. Looks something like that box there. We will see the 7 above it, which would be the atomic number. So that would give us 7. And in this case, we have 7 protons plus 6 neutrons. And that will give us a mass number of 13, which would roll to the top there. So again, this guy would have, in terms of protons, 7. And we had our 6 neutrons, which gave us our mass number there of 13. Lastly, here we switched it up to calcium. So on the periodic table, we would find calcium there. And it does have a 20 above it, which would be its atomic number. So its symbol there would be calcium with a 20 on the bottom. In this case, it has a mass number of 40, which means we can just write the 40 there. Now for calcium here, that means the number of protons would be 20. The number of electrons in this case, since it is neutral, would also balance it out. Again, that gives us our 0 in terms of the charge that's not written there. And our neutrons would be 40 minus 20, which would give us 20 neutrons in this particular case. Any question on any of those? Okay, so to sort of answer the question that was asked earlier, what happens if we do have something that does have a charge? You know, what is changes when we do that? So first off, anything that has a charge are what are referred to as ions. So ions are things that have charges. There's really 2 types of ions. There are cations, which are positively charged, and there are anions, which are negatively charged. So one's a positive charge, one's a negative charge. And it does depend on sort of, you know, what charge you have as to what's going on. We had the one that we just did, which was nitrogen, and it was 7 and 13. And as we saw with no charge, this guy has, once again, 7 protons. It would need an exact same number of electrons, which are negatively charged, to balance it out. It gives us 0. And our number of neutrons would be 13 minus 7, which was 6. Now, if this nitrogen had a -3 charge, the number of protons in this case would be how many? It should still be 7 number of protons, because that is the atomic number. If I change the number of protons, would it still be nitrogen? It would not. So you can never change the protons. So because the protons really determine what element you're dealing with, when somebody gains a charge, the protons stay the same. Otherwise, the element change, and that doesn't happen. So it is, as you asked earlier, it really is the electrons that actually change. So it is the number of electrons that affect the charge that you see. Now, in this particular case, the number of electrons would be how many? Yeah, it would be 10 in this case. And that's because basically 10 negatives and 7 positives leave you -3 left over, which is where the charge comes from. So basically in this situation, you have 3 more electrons than you do protons. So obviously that is why it's negative. So things that have a negative charge, did it gain or lose electrons from the neutral guy? It did gain, yeah. So the neutral guy had 7. The guy that has the negative charge has 10 in this case, and it actually gained electrons. So anions are made by gaining electrons. So something that becomes negatively charged is a result of them gaining electrons. And it's really for that same reason. They basically have more electrons than protons, so they have a more negative charge. How many electrons did it actually gain? That is actually what the number represents. So -3 means it actually gained 3 electrons from the neutral guy. So if you know the neutral guy has an atomic number of 7, and the neutral guy would also have 7 electrons, and it gained 3. So that's how you get to 10 electrons that it would actually have in that particular case. Question on that one there. Now we have our calcium here. Let's say we had our same calcium, but it had a +2 charge. Once again here, in order to keep it as calcium, the atomic number obviously stays the same. So the number of protons here would be 20. The number of electrons in this case would be 18, actually. Now that's because now we have 20 protons and 18 electrons. So 20 positives, 18 negatives. That's going to leave us really 2 positives left over. And once again, that is where the charge comes from. It basically has 2 extra protons than electrons. So those 2 extra account for the positive 2 charge that we actually see. This is a case of a cation. So something that actually will lose electrons and become positively charged because they basically have more protons than electrons are what are known as cations. It is the same sort of reasoning. When you see a positive charge, it has lost electrons. And in this case, it has lost 2 electrons from the neutral guy. So the neutral guy had 20, it lost 2. So 20 minus 2 is 18 electrons it would have in this particular case. So the only thing that changes when somebody gains either a positive charge or a negative charge is the number of electrons. So again, the number of protons cannot change, otherwise you change the element. So it is just those electrons. Question on that there. So why don't we try one? Let's say we had lead with a +4 charge, and we'll do lead like 204. And we'll do sulfur with a -2 charge. We'll do sulfur as 34. So for each of these, how many protons, neutrons, and electrons are there? In case you don't have a periodic table, or you can't see the ones here. Lead is 82. And sulfur is 16. Okay, let's take a look. So going to periodic table, we could get our atomic number, which is necessary there for lead, which is what Pb is. And for sulfur, it would be 16. So starting with lead here, the number of protons would be 82 positive guys. In this case, it does have a +4 charge. So once again, the plus means that it has lost electrons, and the 4 is how many it lost. So really, in a neutral lead, it would have 82 electrons. So less 4 should be 78 electrons in this case. 82 positives and 78 negatives leaves you a +4 left over, which once again is where we do get our charge from. And our neutrons, just like normal, would be 204, which is our mass number, minus 82. Looks like $1.22 there is what we should end up with there. Any questions on that one there? Coming this way to sulfur, getting the 16 from the periodic table, telling us that it is going to have 16 protons. In this case, though, we do have a -2 charge. So when we see the minus, it means that it has gained electrons, and the 2 means that it has gained 2 electrons. So once again, if you look at the atomic number for sulfur, which is 16, and a neutral 16, in a neutral sulfur atom, it would have 16 electrons. So if it gained 2, it should have 18 electrons in this case. That gives us a -2 left over, which once again is where we get the charge from. And our number of neutrons here would be 34 minus 16. And in this case, they're 18, I believe. There we go, 18 neutrons. Any question on any of those there? So obviously you need to be able to know what mass number is, atomic number. You need to be able to write the symbols like this that include the mass number and atomic number with and without charges, and figure out obviously the number of protons, electrons, and neutrons, obviously things with charges and without charges. Any questions on any of that there? All right, so as I mentioned, and as we talked about, isotopes, really the same element, but they do have those different neutrons, which gives them a different mass. In normal reactions, as we've been talking about, really it is those electrons that are involved. So even though the isotopes do have different numbers of neutrons, they really do perform sort of the same chemistry and stuff like that. So it is a very common thing that a lot of elements have radioactive versions of themselves. So in a lot of research, people will use radioactive versions of elements, like say copper. If you were interested in some type of pathway that had copper involved, you could use a radioactive version of it and really just follow the radioactivity and follow where the copper ends up, where it goes. And it will do really the same chemistry as normal non-radioactive copper would do, but it allows you to do those things. Other radioactive isotopes are sometimes used for medicine as well, for imaging, treatment, and stuff like that. They're sometimes used. So they do really perform sort of the same chemistry if they happen to be radioactive than non-radioactive ones does. The next thing we're going to talk about is the periodic table, which in this room is plenty. We got one up here, we got one over there. So the periodic table is obviously an arrangement of all the different elements. It does have a lot of information on it. Sort of elements were put together based on obviously similarities and similar type of properties that they do have. So first couple parts of the periodic table. First off, elements in a column are sometimes referred to as a group or a family. I would say nobody uses family anymore unless you're super old like me, but most people use groups these days. And that is for guys that come down. And if you look at the top of the periodic table where all those sort of columns are, there is a lot of different numbering patterns. So here you can see there's like 1A, also goes to like, 18. That has no numbering on that one. Some of them might even show some B sort of letters on it and stuff like that. Pretty much in all your chemistry career, we use the representative numbering, and that is usually the A numbering when we do it. And what that means is group number 1 is right here. It actually starts with lithium. Group number 2 is there. We actually skip the middle part. This is group 3, group 4, group 5, 6, 7, and 8. So again, groups coming down. Most people don't call it group 1A, group 2A. Most people just call it group 1 and 2, but it's usually thought of as being obviously that A sort of numbering. Now, periods go left to right on the periodic table, and there really is 7 periods on the periodic table. Where hydrogen is 1, 2, 3, 4, 5, 6, and 7. And those are heading obviously in that direction. The number above the symbol, as we've been talking about, is the atomic number, which again is the number of protons that there are in a particular atom. So once again, group 1, group 2, skip the middle, 3, 4, 5, 6, 7, and 8. The periodic table is really broken up into 3 sort of categories. On most periodic tables, you can find this what's sometimes referred to as a staircase here, kind of coming down. Sometimes boron is there as well. And kind of to the left of the staircase are metals. To the right and up are non-metals. And the staircase are what are referred to as metalloids or semi-metals. And metals are good conductors of heat and electricity. They also can be hammered into thin sheets. They can be pulled into wires. They typically have a shiny appearance. Pretty much most metals are solid at room temperature. The exception is mercury, which is usually a different color. So that one's blue. That one has a green box over it, which means that it is a solid. And that's usually what you see here. But pretty much all other metals will be solids at room temperature. This is hydrogen right about here. Why is hydrogen not part of group 1? Hydrogen is what type of element? Is actually a non-metal, even though it's hanging out with all the metals over there on the left-hand side. Although in a lot of cases, it can behave similar to metals in terms of how it reacts and we think of it. But hydrogen actually is a non-metal, which is why, again, group 1 actually does start with lithium, which is underneath it. They don't print them too much like that anymore, but years ago, they used to print those big periodic tables and actually put hydrogen over here as well. You'd actually see it on both sides of the periodic table, but most nowadays, they actually don't do that very much. But hydrogen is a non-metal, but it is over there kind of hanging out on top of group 1, actually. Non-metals, as you could probably imagine, are pretty much the opposite in terms of characteristics of metals. They are poor conductors of heat and electricity. They also are a wide variety or more variety of states. Some are gases, some are liquids, some are solids. A lot of the non-metals are those diatomic molecules that are elements that we talked about, like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all these guys that come as 2s, basically. So a lot of those sort of diatomic molecules that are elements are non-metals. The semi-metals are metalloids, which are more commonly called, is that staircase that comes down. Some books will include boron as well as being part of that, and some don't. Can't remember off the top of my head what yours does. But you can kind of see the metalloids, which are these blue guys here. You know, they're kind of to the right are non-metals, to the left are metals. And by the way, the 2 rows on the bottom are also metals. So the semi-metals pretty much have properties that fall basically on both sides. So the same element will have some properties that are considered metal type properties, and the same element will have some properties that are considered non-metal. So semiconductors and stuff like that. So they kind of have properties that kind of fall on both sides, kind of make sense where they're sort of located there on the periodic table. Now, some groups do have special names. So starting here with lithium, which is group 1, it is the alkali metals. Right next door at beryllium and coming down, actually beryllium here, coming down, are the alkaline earth metals. Pretty much alkaline means basic. So a lot of the strong bases that we come across, things like sodium hydroxide, potassium hydroxide, calcium hydroxide, come from group 1 and group 2 on the periodic tables. A lot of really strong bases come from that area. Coming over here to group 7, which is right here. That is halogens. So those are your fluorine, chlorine, bromine, iodine, those guys that come as 2s. And right next door are your noble gases, your helium, neon, argon, krypton, all your ons there are our noble gases. Noble gases are chemically inert. They don't react with many things. They will react with themselves, but pretty much not other things. So you do need to know where the alkali metals are, alkaline earth metals are, halogens, and noble gases. Question on that there? Now, the halogens, as I mentioned, do come as those 2s, and a lot of them are gases like the fluorine and the chlorine, yellow and green. Bromine is kind of like a vapor over a solid. And you remember the experiment you did a couple weeks ago with the iodine when you heated it, all that purple that came up. So that is your iodine. They also make acids, as we'll talk about. Hydrochloric acid, hydrobromic acid, hydroiodic acid are all those guys with hydrogen. They're very reactive as well. There's our noble gases, again, group 8, sometimes called rare gases, but most people just call them noble gases this day. Now, these two rows on the bottom, this is the lactonide and actinide series. And if you follow the numbering on the periodic table, they actually go right here. So that's 57 and 72. So here's 58, that should go there. And that's 89, and there's 90. So these two rows technically should go right there between those two elements. They typically don't do it because it makes your periodic table much like this one. Why do you need like a wall to kind of do that? So they kind of put it there in the right spot, but it makes it obviously too wide. That's where you find a lot of radioactive elements, a lot of man-made elements as well, are on those two bottom rows. They're called the lactonide and actinide series because that's technically who they follow on the periodic table and where they should go. Now, between group number 2 and group number 3 on the periodic table, that is where we find our transition metals. And our transition metals can have multiple or varied type of charges. And that is those elements that are in blue here on the picture between group number 2 and group number 3 on the periodic table. That's why also the bottom two rows are sometimes referred to as the inner transition metals. Because technically, as we just talked about, that is where they should go. So they kind of fit in that spot. So obviously, again, you need to know where transition metals are as well. Any questions on that? Now, the characteristic shape of the periodic table, again, was put together to keep things that are similar to each other, near each other on there. And obviously, as we move from kind of left to right on the periodic table and up, we go from a more metal area or property to more non-metal, heading up and to the right on the periodic table. There are some noble gases, noble and noble gases. There are some very unreactive or noble metals, and that is gold, silver, and platinum. And that is basically right here. Where we're at there. Those guys. So gold, silver, and platinum are also very unreactive. Gold pretty much doesn't react with much, which is why it's expensive, because it doesn't react. All right. Also, a major difference between sort of the noble gases and like hydrogen, oxygen, and those type of things is group 8 gases are sometimes referred to as being monoatomic, which means they come as ones. So basically one atom for each of those guys is how they come, as opposed to something like hydrogen that's diatomic that comes as 2 hydrogens together. So something like helium, neon, and all those guys basically all come as ones. And there's our diatomic guys that we've talked about. And some there. Any questions on the periodic table? So clear, you need to know groups, which way they go, the group numbering, which way periods go, the names of the groups, where transition metals are, where metals, non-metals, and metalloids are. Any questions on any of that? Okay. So let's talk a little bit about some non-metal characteristics. It is possible to have some different forms of some non-metals. And those are what are referred to as allotropes. So if you have sort of a different form of the same non-metal element, that's referred to as an allotrope. Common example is carbon. Carbon could come as a diamond, come as good old graphite like pencil lead. Also could come as a fullerene, depending on which one you get, different price point. Hopefully, you know, if you have a diamond, costs a little bit more because of the arrangement of the carbons. But maybe yesterday you could have passed off some pencil lead going, hey, it's just the same carbon as a diamond. It's all good. But graphite is basically layers of carbon. So it obviously has properties like diamond, then obviously graphite or something like that. Fullerenes, by the way, are really large groups of carbons together, like 60 or more. They kind of have a shape like a soccer ball. They're sort of arranged like a soccer ball looking thing, are those fullerenes. And they're all basically carbon, so they're all different forms of carbon. Now, we talked about a little bit earlier ions, and just to reiterate a couple of things on it that we talked about. We kind of jumped a little bit ahead. First off, when we have an ion, it does have a charge, and as we talked about earlier, things that have a positive charge are referred to as cations. They are a result of losing electrons, and for the most part, those are going to be your metals, or typically the ones that like to give away their electrons. You could represent a metal losing an electron with a chemical equation, like we see here, and we could write something like sodium that has no charge. And when it does lose an electron, it will become a positive one charge. And what we see here is our electrons on the product side of the arrow, or the right-hand side. And that is the way that we represent the element losing an electron. Same thing with magnesium, as we see down here. Magnesium with no charge will then become magnesium with a +2 charge and lose 2 electrons. And again, we represent that by the electrons being put on the product side like they are being given off. If we wanted to actually name just the ion by itself, so if we had something like the Na+ ion and we wanted to give it the name, the way that we name things that are cations is simply we just use the name. So this would be the sodium, and we typically would put ion because it does have a charge. If we had Mg2+, this would be the magnesium ion because it has a +2 charge. So things that are cations that have a positive charge, we simply just use the whole name of the element and we add ion to it to name the cation what it is. Just like this guy here, aluminum with a +3 charge would be the aluminum ion. So we simply just put ion at the end of the name. Question on that. So each of these guys have lost electrons from the neutral atom. And again, the number of the charge is how many electrons it lost. So sodium lost 1, magnesium lost 2 electrons, and aluminum with a +3 charge has lost 3 electrons. Now, anions, as we talked about, are guys that do gain electrons. And we could also represent that with an equation. So for example, if chlorine gained an electron, it would make chloride ion there. And different though, the electron would be on the reactant side. So if we were to write an equation to represent it gaining an electron, it's on the reactant side like it's being added to it. And that would make our -1 charge there. Same thing if we had oxygen. So oxygen plus a couple of electrons will give us an oxygen with a -2 charge. So again, electrons would be on the reactant side here. How we name negative ions or anions, if we wanted to just name the anion, is we take the root of the name and then we add IDE to the end. So we drop the last part of the name and we put the IDE there. So instead of chlorine, we drop it and we have the chloride ion for Cl-. For O2-, that is oxygen. We drop the last part of oxygen, and that would be the oxide ion. If we had S2-, that is sulfur. We drop the last part of sulfur and put IDE. That would be the sulfide ion. So things that have a negative charge gets the IDE at the end of it. We drop the last part of the name, sometimes more or less of the last part. And that's how we get a name like this. Sodium chloride is what this is named. Sodium chloride. This is a formula for an ionic compound that really represents a sodium ion and a chloride ion together. So whenever you put a positive guy and a negative guy together, the overall charge should always equal 0. So +1 and -1, you just need one of each of them. By the way, as I mentioned before, that is really the only time that they do have charges. So if you have just some element by itself, it does not have a charge. It's only when metals and nonmetals come together that they actually start to gain charges. So if you have a sodium piece of metal, no charge. If we put sodium and chlorine together, they both will have a charge. Any questions on that there? Now, when things do get charges, there are certain things on the periodic table that can have sort of fixed charges. Everybody in group 1 has a +1 charge. Everybody in group 2 has a +2 charge. Really, aluminum here has a +3 charge. And then we kind of skip group 4 as the kind of semi-metals come down through there. Starting at group 5 actually has a -3 charge for the non-metals like nitrogen and phosphorus. Group 6 has a -2 charge. Group 7 has a -1 charge. So it's kind of like +1, +2, +3. Skip -3, -2, so up to 3 and then back down to 3. There are a few transition metals that, even though they are transition metals, they do have sort of fixed charges. Most transition metals will have a variety of charges, but zinc and cadmium, they are always going to be +2. And then if you hang a left there to silver, he will always be +1. So those 3 transition metals, even though they are transition metals, actually do have fixed charges. Everybody else in the transition metal region, and even kind of in this region as well, will have a variety of charges. They could be +2 or +3 in certain situations, depending really on the situation. Any questions on that there? Hydrogen, as we will talk about, which is here, can actually be +1 or -1. So hydrogen is an interesting one. It could actually go both ways. It could be +1 or -1. Any questions on that there? All right. Now, because ions are present and they do have charges, they can complete sort of the electrical circuit. And when you dissolve a solution that produces ions, it actually can conduct electricity really well. And that's what's known as an electrolyte. So an electrolyte is something that, when it's dissolved in solution, creates ions and conducts electricity. There are a few different types of electrolytes. There's a strong electrolyte, which 100% breaks apart into ions. So for example, if you had some sodium chloride solution, you would have sodium ions and chloride ions. And in solution, you would have 100% just the ions floating around. And because you would have generated a lot of ions and none of the sodium chloride units would stay together, it would all just be ions. It will conduct electricity really, really well. So if you took like electrodes that's hooked up to a light bulb, put it into the solution, the light bulb would turn on and be very, very bright. So it would conduct electricity really, really well. There's also weak electrolytes, which basically stay together, but do produce a few ions, like hydrofluoric acid. When you have hydrofluoric acid in a solution, it mainly will stay together as the HF unit, but it will produce a little of these guys, of the actual ions. So since it's able to still produce some ions, it's able to still conduct electricity. It just can't conduct electricity as well as a strong electrolyte. So if you take the light bulb example with electrodes hooked up to a light bulb and you put it into it, it would turn on, but it'd be like super dim. So like barely, like the light bulb barely on, it would still be able to conduct electricity. And then there's things that are sometimes considered non-electrolytes. They dissolve, but do not produce ions. So for example, if you took sugar, sugar would dissolve in water. Sugar is carbon, hydrogen, and oxygens. They do not break apart. They do not produce ions, but it definitely will dissolve. But because it doesn't create any ions, if you put the light bulb example in there, the light bulb would not turn on. It does not conduct electricity. So a strong electrolyte completely breaks apart into ions, conducts electricity really well because of the lot of ions that are present. A weak electrolyte pretty much stays together, but does break apart a little bit. And because it has a little bit of the ions, will conduct electricity, but not very well. And a non-electrolyte will dissolve, but not produce any ions And because there's no ions present, it would not conduct electricity. If you had pure water, nothing but water, is it a good or bad conductor of electricity? It is a bad conductor of electricity. So if you have pure water, has no ions in it, like deionized water, in theory. So it will not conduct electricity. Just safety note, the water that comes out of your shower is not pure water. Yes, they actually put ions in it, and you will fry yourself if you decide to blow dry your hair while you're taking a shower. Yes, so you will electrocute yourself. But if you have pure water, it's actually a bad conductor of electricity. As we see here, light bulb doesn't go on. If you put some salt, which is sodium chloride, the presence of the sodium ions and chloride ions in there will make this conduct electricity really well, and the light bulb will go off really brightly. Again, if you have a weak electrolyte, that's going to be kind of dim, and a non-electrolyte will be like the guy here on the left. It will not go off. So to finish up here, this chapter, a couple important things, and some of the stuff that we talked about. Whenever we take anything that is a positive ion and negative ion and put them together, that is what's really referred to as an ionic compound. And that's basically a positive ion and negative ion that comes together. And when we do that, we always want to put the ions together in whichever way gives us a value of 0 and the simplest way to do it. So our sodium chloride example, Na plus, Cl minus, +1, -1. You just need one of each of them to write the actual chemical formula for sodium chloride. The chemical formula for an ionic compound should not have a charge. Again, it should balance out. If I take something like my barium, which has a +2 charge, or my oxide, which has a -2 charge, when I put those together, +2 and -2 equals 0. So I just need one of them. If I take something like my aluminum and my sulfide, if I were just to put those together, one of each, what would I end up with in terms of the charge? We would end up with a +1 charge, right? And we can't do that. So the common number between 3 and 2 is 6. So to get the aluminum to 6, you need 2 of them. To get the sulfide to 6, you actually need 3 of them. So +6 -6 balances out, gives us a proper form of Al2S3. And same thing with our potassium here, +1, and our phosphide, which is -3. In this case, we'd actually need 3 of the potassiums to come together to give us +3 to balance out the -3 that we see there. And that would give us a form of K3P. Now, sometimes people are taught to just simply move the charges down or move the subscripts up and exchange the spots. And if you do that, you can't do that blindly, and you'll be good like 93% of the time. It won't work 100% of the time. So it's better to think of it more as a sort of a math problem to balance out the overall charge. Any questions on that there? All right, wrapped up chapter 4.